everybody. Today I will talk about mainly the fundamentals of the iMachining patent, and I'll try to explain how iMachining does what it does. What you see here on this screen are the three ingredients of iMachining. We have iMachining 2D, which we'll talk about today, then iMachining, which is for prismatic parts, and then next week we'll talk about fundamentals of iMachining 3D, which can be used for machining any complex 3D part, and obviously it's an easier way to machine also prismatic parts. Always we say the third ingredient from iMachining after iMachining 2D and 3D is the wizard. Because basically if iMachining was only about an advanced toolpath, it will be really a very small story, because it's very difficult for the customer to choose the feeds and speeds at which to work. But iMachining gives you more than this advanced toolpath that we see here on the left, the morphed spiral toolpath, which I will explain further later. It works together with the wizard, which provides optimal feeds and speeds at every point of the toolpath, taking into account the stock, and the tool material properties, and also the machine specifications. So this combination enables you always to guarantee first part success. We take the responsibility to give you the best toolpath and also the optimal feeds and speeds. To summarize the advantages of iMachining, first, increased productivity due to shorter cycles, time savings of 70% or more. And this has been proven in more than 3,000 customers already working with iMachining worldwide. And you can find also in our website about 170 actual success stories of customers who saved great amount of time using iMachining. In addition to saving so much time in cutting, we say iMachining produces dramatically increased tool life, and really this is dramatic. Sometimes up to 5 times more tool life. Like for some part, it might take one tool to cut it, but then with iMachining, with one tool you could cut 5 parts. Is that dramatic? In addition, it has unmatched hard material machining speed. When you have hard metals like titanium, iMachining saves you tremendously, and we'll see this in examples. It provides outstanding small tool performance. When you are cutting with very small tools, iMachining really excels. And we have a lot of customers in the medical industry using small tools and working with iMachining. Another important point, high programming productivity. Because it's easy to work with iMachining, you can program many more parts per day. If you have different parts to program with iMachining, then you can just using our standard 2.5D milling. And we guarantee you it has the shortest learning curve in the industry. It's so easy to learn iMachining. Let's talk about the main points of iMachining. Let's first look at what are the main 3 problems with the standard toolpaths in 2.5D milling. The offset toolpaths, I call them, in pockets. First, it's overloaded tools. As you see this tool here, it's cutting with a 180-degree angle. And this produces a lot of pressure on the tool. This comes from, if you look at the picture to the extreme right, you see the standard offset toolpath of pocket. As you see in the corner where the toolpath suddenly changes about more than 90 degrees, about 90 degrees. Here is the biggest resistance to the tool, and that's why what you have to do when you do such a pocket, you have to reduce your feeds according to this point where you get the biggest force on the tool. As a result of it, when the tool is cutting here on the line where it could move faster, it doesn't move fast because you have standard feed for all the toolpath. So the weakest point in the toolpath forces you to work with slower speeds. And if you look in the middle, another major problem people hate is when you are cutting air and not metal. It's total waste. iMachining solves all these problems. If you look at the toolpath, both in the picture on the left, where we have an open pocket, and we see more a toroidal toolpath, which I'll talk about later, or in the extreme right picture, where you will have a closed pocket and a morphed spiral toolpath. As you see, the toolpath is always tangent. There's no sudden change in the direction. And this is really the main type of toolpath that iMachining produces. And we will see how this toolpath is produced. And another major advantage of iMachining, what you see in the middle, is exact stock machining, no air cutting. Air cutting is reduced really to the minimum of the minimum. We'll see in the examples. So basically, with iMachining, there is a limit of the cutting angle. It cannot go above the maximum cutting angle, let's say here 80 degrees, and not below a minimum cutting angle of 20 degrees. So all the time, while the iMachining toolpath is cutting, the cutting angle is changing between these two extremes, between 20 and 80, but never above 80. So what happens if the cutting angle is increased to 80 degrees? Obviously, the force applied on the resistance to the tool become bigger. So the feed rate is reduced, as you see here. When the angle is 80, the feed rate is reduced to 1,675. But when the tool is cutting only 20 degrees, like the picture on the left, the resistance to the cutting is less, so it could move faster. Here we see we have a feed of 3,792. So all along the toolpath, while the cutting angle is changing between the minimum and the maximum, the feed rate is always changing all the time. So that the net result is there is always a constant force applied on the tool. If the cutting angle is small, the feed becomes big. If the cutting angle is big, the feed becomes small. And we are the only CAM system that really knows what is the force applied on the tool at every point. And that's why we are able to guarantee you first pass success. And that's why how the wizard is able to give you the optimal feeds and speeds. Because we know what is the constant force applied on the tool all the time during the cutting. Let me explain now about the shape of the toolpath. As you see in the picture on the left, you have here a rectangular area which we want to cut. Now, if we are using a regular spiral, which is circular, obviously you cannot cover the whole area with a circle. It will reach some point and can't cover it. So what we do, what we call a morphed spiral. We kind of squash the spiral so that if you see in the short direction, there's small step over, but in the longer direction, there's a bigger step over. So by using the morphed spiral, we can cover not only circular areas, but any shape area by changing the characteristics of the morphed spiral. But still, if you look to the picture on the right, there are some shapes you can't cover with one spiral, with one morphed spiral. Like if you take all this rectangular area, you'll have to squash the spiral so much that it won't be any more effective. So in this case, this is the second main characteristic of the iMachining patent. By the way, the iMachining is patented all over the world, and we have protection against people trying to imitate us. Although, even if we didn't have a patent, it will take them years and years to try even to do something similar to us. What you see here on the picture on the right, what we have what we call intelligent separation. iMachining looks at this long rectangle and decides it cannot be done with only one morphed spiral. So it uses channels, as you see here in the white. These are toroidal toolpath channels. it uses these cuttings to separate this long area into 3 sub-areas. And then each of the sub-areas is done using a morphed spiral. So in the end, this whole pocket is cut by a combination of morphed spiral toolpath and toroidal toolpath in the channels. But obviously, the most efficient is the morphed spiral. So always, iMachining tries to do the maximum with morphed spiral. If it can do it, will do 100% with morphed spiral. If it cannot, as in this case, it used the toroidal to do the channels, or sometimes it uses toroidal to do some of the rest machining. But always, the morphed spiral is about between 80% to 100% of the cutting. And this is the most efficient toolpath. Let's look here at a typical example of electronic box, how the toolpath develops. So it starts here in the center as a morphed spiral, as you see, and then it meets the 2 islands. So it generates separating channels around the 2 islands, and then you see again it continues to a morphed spiral until it meets this other island here on the left. So here again it generates a separating channel around this island, and then it continues again to spiral. This is all done automatically, and another major advantage of iMachining is that not only it does the rough, but only it handles also the rest material in 2.5D machining, and then it does also a finish cut, as you see on the bottom right. So with iMachining 2D, you can complete the pocket with the roughing, the rest roughing, and the finish. We are the only system that can do that using this type of toolpath. Here we see another example where each one of the pockets is a closed pocket. You see the tool went in a helical way, and then it started doing a morphed spiral. But then when it reached this narrow area, it moved to toroidal. So each one of these pockets was done as a combination of spiral and toroidal. In the middle, you see it started with spiral, but then continued mainly in toroidal because it's something very long and thin. Let me look just for a few seconds at some actual cutting to show you the results. I'm sure all of you have seen such videos, but let's look for a couple of seconds at this cutting of the steel part. As you see, iMachining cuts very deep, but with a small cutting angle. Now it's going in a helical way inside the material, and then it will start with the iMachining cutting. This is cutting steel, remember. Here we are seeing it in slow motion. As you see, the chips are always the same size. Okay, so now we looked at the toolpath. Now let's look at another major aspect of iMachining, the wizard. If you are doing the cutting without iMachining, and you wanted to guess the feeds and speeds that are the best, you have to take into account all the following properties. First, the material properties. Clear, the hardness of the material and the other properties. Also the properties of the tool. Obviously the depth also that you are going to cut. And then last but not least, the machine specification, maximum spin allowed, maximum feed, maximum power. So you can imagine trying manually to think about all these parameters, take them into account, and to guess the optimal feeds and speeds is mission impossible, even if you have tens of years of machining experience. You always meet a new material that you didn't cut before, new type of tool, new machine. Well, with our wizard, we take the guessing out of the game. Because since we generate the tool path. And as I explained to you, we know how to keep a constant force on the tool the whole time. Basically, we can calculate the optimal feeds and speeds. Taking into account the depth of the geometry, the tool properties, the machine properties, and the material properties, we give you at every point of the iMachining toolpath the optimal feed and spindle speed and the depth. Obviously, the only thing you have to do is to choose your material and your machine properties from a database. And obviously, you choose your geometry and the tool, and then we calculate the rest. The only aspect of the wizard that you have to control is what we call the machining level. As you see here in the picture on the right to the top, there is a slider that has 8 positions from 1 to 8. These are levels of aggressiveness of machining that you want to make. So the question is, why not always go to level 8? Because sometimes it's a new material that you are cutting and you are not so sure that you want to, the first part you cut, to work at the maximum speed. You might be not so sure of your clamping, that it is sturdy enough to work the fastest. So always, you could first cut the first part using machining level 3 or 4, and then, looking at the results, you could increase it to 8, and could even have 8 turbo. It's even faster. So, as a user, this is the only thing that you have to control about the aggressiveness of machining, and then machining does all the rest, iMachining. We tell you that we guarantee always iMachining first pass success, because we are giving you everything, the tool path and the cutting conditions automatically. Another point that the wizard makes sure of, since we are cutting deep, and this is one of the characteristics of iMachining, we always cut deep and fast, but small cutting angle. We make sure that the ACPs, the axial contact points, are an integer number, like 2 or 3 or 4, so that there is enough support for the tool to avoid vibrations. Just a small example of a cutting we have done in the UK at a company called Gardner Aerospace in titanium. They were using CATIA, CAM, and to cut this pocket you see here in titanium took them 14 minutes. Our reseller in the UK came with iMachining, and he cut the time from 14 minutes to 3.5 minutes. Unbelievable, but this is the case. Let's look at some more examples. Here is another customer. There is a misconception that iMachining is good mainly for cutting hard metals. Not true. With aluminum, you could also save a lot. Here is an example of iMachining 2D cutting in aluminum. Customer had 400 pieces to produce. His standard cutting time using our standard 2.5D milling was 17 minutes. With iMachining, he reduced it to 6 minutes. 65% saving, and total cycle time saving for 400 pieces, 73 hours of machine time. And obviously, we didn't mention it here, he used much less tools to do the cutting. As we said, iMachining saves a lot in tool life. Let's look at another example of a customer cutting in titanium. He had 75 pieces to produce. His standard cutting time with our 2.5D was 17 minutes. With iMachining 2D, he cut the time to 3.5 minutes. Even more saving than in aluminum. In titanium, he saved 80%. And for 75 parts, he saved 16 hours and 52 minutes. Unbelievable savings, but these are true customer stories. And now Sydney will take over and show you some more such stories with actual looking at the software itself. Sydney, take over.
Okay, do you see my screen? Okay, one moment, please. Okay. There we go. Okay. What we're going to do now is I'm going to be showing you a couple of parts that I have. Now, these parts that we have that I will be showing you are actual parts from our customers. Now, what I'll be showing you is as follows. These parts, they first were cutting it before they had iMachining. They were first cutting it using the conventional 2.5D pockets and profile operations that we have in SolidCAM. And then we came along with iMachining and showed them what they did in iMachining, and then they programmed the parts in iMachining. And as we go through the parts, we'll see what kind of savings it actually had on the parts itself. Now, this first part that I'm showing you over here is a part that's made of 4340 is the material. We know that's a kind of a hard material. In this particular case, the 4340 was at a 40 Rockwell, and he had to do a total of 200 of these parts. Now, obviously, when you're doing that amount, you're trying to save as much time as possible. And he started programming the parts using a face mill operation, and then he started with a pocket operation. Now, let me go into the pocket operation itself, and we'll note that if I open up the pocket operation, what he first did over here was very simple. If we take a look at the geometry, he first milled out this area over here using the pocket operation. We're not talking about machining around the whole part right now. We're just talking about this area, the first area he had to clear out. He had to create a geometry. He made a sketch around part of it over here to create the geometry, having this part as an open part of the geometry itself. Okay, this is the area that we started to work in using the regular profile, the pocket operation. The tool that he used over here was a 12 millimeter end mill that was outside of the holder by 60 millimeters. Now, if you also go into the data of the tool, you can see that he was working at a feed rate of 450 millimeters per minute, which is pretty aggressive when you're talking about this type of material, but not as aggressive as we could get. The reason why it couldn't go any further to be more aggressive, we'll see that in a few moments. If we go into our levels, you'll note that our pocket depth that has to go down is 40 millimeters. Now, cutting into this type of material, the maximum step down that he was able to go down without causing any problems to the tool itself was 4 millimeters. And if we take a look at the actual simulation, and I'll use Solid Verify to show the simulation itself, you'll see the following. This is the actual stock material as shown over here. This is actually turned out with a dovetail in the back to go into the fixture itself. And we'll start step by step. If we go step by step, you'll see the tool goes down. And the first thing it does when it gets to its depth at -4, it goes into the material itself. Now, at this point, you can see that we're going with the full 180 degrees of the tool into the material itself. With the full blunt of the tool right into the material itself. When doing so, you cannot go fast, and you cannot go to the full length of the tool. If you would do that, this would cause a lot of vibration on the tool itself. So you can only go a certain amount, a small amount as far as depth goes, and your feed rate has to be limited because of this condition. So this is exactly what happened in this particular case. Now, as we go around the part itself, you'll note that it always has those areas when it goes into these areas and the corners. Let me actually stop now it's getting close to those areas itself. We can see this over here. You see it, there's always times where it goes into areas or such as those corners with the full blunt of the tool, the full 180 degrees. So we constantly have to watch to make sure that we're not going too fast, or else we may end up breaking the tool. So this causes us to work, this forces us actually to work a lot slower than we would like to. Okay, now let me actually run the entire simulation of everything that the customer did. And what we'll note in particular is the actual machining time. The actual machining time that he had was a total of approximately 44 minutes as shown over here. Now remember that value, because we're going to get back to it later on. Okay, now that we did that, let's see exactly what we did when we went over to iMachining. Let me take these operations over here, and I'll suppress them so we can see just the operations itself that we did over here. First we did the following. We went and did, instead of the face mill, we replaced that with iMachining on both sides. I'm just going to show you right now the tool pass that we had on both sides. What we have on this side is exactly what we have on the other side. But I'd like to go now into the actual next operation and show you some of the parameters that we used inside the next operation itself. The next operation, if we go into it, and we'll take a look from the top view itself. First, let's take a look at the geometry. The geometry itself includes this entire area, this area outside over here, as well as this area in here, and this area inside. This is all one operation being done on this area itself. Okay, so that's as far as our geometry goes. The tool, you can see it's also sticking out of the holder at 60 millimeters. Now let's go to our levels. You'll note that we're going to a depth of 42 millimeters. Now remember, last time we went down every 4 millimeters when we were going down. But now if I go into my technology wizard, you'll note the following. The technology wizard automatically will give it a step down of 21 millimeters. This itself is based on two factors. One, if I go back to the tool, the cutting length of the tool itself. That was 24 millimeters. And the level that has to go down, 42. So by taking that into account, the technology wizard automatically recognizes that it can go down 21 millimeters each time, divided, in other words, having that 2 times. So it covered this in 2 down steps. Now also note the following. The feed rate over here, a lot quicker than that 450 millimeters that we had before. Now, not only that, let's take a look at the machining level. I'm traveling right now at a machining level of, I'm using an aggressiveness of level 5. Okay? Not too aggressive, not too shabby either. If I were to actually bring this down, you can see the values over here change. Okay? The more aggressive I get, the values over here go higher. This is automatically calculated within the wizard itself. Also, we should note one more parameter inside the wizard itself. That's the cutting angle. This is exactly what Emil was talking about before, is we control the minimum and maximum cutting angle, the actual engagement angle of the tool into the material itself. Now, I'm going to run the simulation, and as you run the simulation, we're going to take a look at a few aspects of the cut itself. I'll run the simulation of this particular operation itself, and then we'll run it on the entire part. Now, as you see, the tool is going down. One step at a time, I'm going to do this. Note it's going down 21 millimeters. Now, if we take a look at the tool itself, as it's doing the contact into the material itself, you'll note, look at the cutting angle. It started off at a smaller cutting angle, and it's going up to its upper cutting angle itself, as shown over here. You can see over here it's going up to a cutting angle at 68 degrees. Okay? As it's going around the part, you can see at points it changes, gets lower. Now, as it gets lower, the feed rate also gets higher. This keeps a constant chip load on the tool itself. By doing so, that you're not getting any kind of vibration on the tool. By doing that also, you're also making the tool life a lot longer. You're causing the tool life to be a lot longer because we all know that what actually is a no-no for the tool, what actually breaks up the tool is vibration. This is exactly what we're avoiding over here. By keeping a constant tool load on the tool itself, you will not get any vibration, and therefore everything will be equal all along, and you'll always get that nice smooth cut without any kind of vibration. And because of that, your tool will last a lot longer. Now let me actually run the simulation on the entire part. As you see, we did the bottom over there. In a moment you'll see it'll go up to the top itself, as shown over here. Doing that trochoidal tool path on top, going from one side to the other because it has a wall over there. So doing its complete trochoidal cut. And then doing what I showed you before. And not only that, but you'll see now it's actually doing a finish cut around the part itself. First clearing out the corners, and then going back to the beginning, as shown over here. And then doing a finish cut around the entire part. Now, take a look at the time. The time here is just under 7 minutes. If we remember what we had before, with the regular standard milling, we had approximately 44 minutes, but compared to what we have now of about 7 minutes, you're saving at approximately 84% in this particular case. In this particular case, this is how much was saved. Try figuring that out among 200 parts. Well, we'll talk about that at the end, exactly what was saved over here. But now, let's go to our next part. I'll close this part that we have here, and we'll open up my second part. Now, this particular part is a typical deep electronic box. Now, this electronic box is made up of aluminum. And as Emil had mentioned before, the savings is not only on steel or titanium, it's also on aluminum as well. And this is exactly what happened in this particular case. Now, what's so special about this particular electronic box is that the area, the pocket itself that we have over here is very deep. It's approximately 113 millimeters deep. So immediately that's telling us that we have to work with very long tools. And even in these areas where we have smaller radiuses, we have to work with long tools. And because of that, we cannot take large step down, and we cannot work too quickly as well, even though it's aluminum. Okay? So let's first take a look at the operations that the customer himself did. Now, in this particular case, he had to do a total of 140 parts in this batch run. Okay? Now, we have, of course, drilling operations that he had to do at the beginning and at the end, but we're going to concentrate now on the operations that we replaced for him. Now, we first started out with the regular pocket operations and the profile operations. Let's take a look what was done over here in the simulation itself. We'll run our simulation, again using Solid Verify, and you'll see the first tool that he particularly used in this particular case was actually a face mill to cover as much ground as he can, but with the face mill you can't go too deep. So he went as deep as he can possibly go in this particular part with this tool and covered the entire depth of that particular part over there. using this tool. As he goes further down, we'll show this in a moment, he uses longer tools to get down to those corners itself, using profile and pocket operations to clear everything that he needed. Now, if we take a look at the time in this particular case, it took him 2 hours and 16 minutes to do this particular part. Okay, and we're talking right now just about the profile and pocket operations. What I'm going to do now is going to load the part again, but this time with operations done in iMachining. When we came back to the customer with the iMachining, this is what the result was, and this is how we actually cut the part at the very end. Okay. If I were to just show you right now just a tool pass on this first operation over here, if we can see it, you'll see that as Emil had tried to show you before in the diagram, it's actually doing a tricordial tool path over here, and then in the corners when it finishes doing that morph spiral tool path over here, and at the end then it goes into tricordial tool path. Actually, let me run the simulation, and by running the simulation we can see exactly what's going on over here. I'll do this slowly, and what's happening at the very beginning is as follows. First of all, as it's going into the part itself, it's actually doing a helical cut into the center of the part. In other words, if you didn't have a drill operation done here before, no problem at all. It'll just do it automatically using the helical cut into the part itself. Once it gets to its depth, what's it's doing right now, it's doing that morphed spiral cut into the part itself. And also note what happens with the feed rate. The feed rate, as it's running in these areas, is higher, and these areas where it's a thicker cut, it's running slower. So the load on the tool is constant. Okay, and you can see the cutting angle being changed from its minimum to maximum throughout the part itself. Let me go now a little faster, and you can see is doing that constant morph spiral, changing the shape of that tool path itself, but keeping the constant spiral over there. Now note, once it gets to its maximum that it can with the spiral, now it's actually doing that tricordial cut into those corners over there. Same thing over there. Now let me stop it over here and do this now one step at a time. As you see, you can see the control that is taking as far as the cutting angle. Complete control of the cutting angle, no chance of it ever going into over-engagement of the tool itself. Continuing on the part, you can see that going through that entire area over here, going down now to its next step, and because it works this way, you can go down each step down can be much larger than we had in the previous cases. Let's run this now towards the end, because by the way over here, not only are we doing regular cuts, regular rough cuts, but we're also doing rest machining as well to clear out the corners. And we'll get to that in a moment as we get towards the end of those rough cuts as shown over here. Going down to those pockets at the very, very bottom. And now it's going to start doing the rest machining into the corners itself. And you know it's working with a very long tool but a small tool. But because of the way we can work a lot faster than you were able to do in your regular 2.5D conventional method. Now, the total time in this case was approximately 45 minutes as shown over here, as compared to 2 hours and 16 minutes we had before. In this particular case, it was a savings of approximately 67% of what we had before. We'll get back to the amount we saved between the two towards the end, but now let me get to the next part. The next part I'm going to show you will be this part over here, which is also a part where the material was 4340 with a 40 Rockwell on the part. So again, it was a pretty tough part. Okay. Now the batch run in this particular case, he had to do 120 parts in this particular run. Well, again, we'll show you first how he programmed it using the 2.5D conventional method before he had iMachining, and that's over here itself. Now let me just run the simulation, and we'll do this again one step at a time, one operation at a time. The first one, well, that was a regular face mill, which we've also done in our next after that. Now we also did a drilling operation, because we have a pocket later on to do over there. And now he did the following. You'll note that what's happening is he's working on the corners in this particular operation. Instead of doing a complete profile around, he avoided that, because if you do a regular 2.5D operation with a regular profile operation, you would have a lot of air cuts around. So he was actually being as efficient as he possibly can by breaking it up into different operations. But each one of those is a separate operation, something that we do not have to do in iMachining, and we'll see that in a few moments. As you can see, he did every single corner as shown over here, every single area that he had to go really deep. And then at this point, he was actually doing a regular profile operation going around the part itself. Now, note, now he's going to do his pocket operation inside over here. Now, he'll go down into the hole that he drilled out, as shown over here. Then, however, when it actually goes into the material, he's going with the full blunt of the tool into the material itself, so he cannot take deep cuts. We'll run it again towards the end in this particular case. You can see that this is the entire part being machined, and we'll take a look at the time. The time in this particular case was 26, almost 27 minutes. Okay? Now let's take a look at how he did it afterwards once he had iMachining. Let's just suppress these operations over here. Here we go, suppress. And we'll run a simulation with the iMachining operations. Now note, we have our face mill, we have our drilling operation, as shown over here. But now note what happens with the iMachining. Remember previously, he did each of the corners and these areas separately. This is going to be done now in one simple operation of iMachining as shown over here, where it first clears out the corners automatically. It knows where there's extra material over there. So first those trapezoidal cuts in the corners, making way for it to work as it's showing now, doing that spiral cut, that's morphed spiral cut around the part. So we try to get as much as possible and that spiral cut over there. The same thing over here. He'll go into that hole automatically and do the spiral cuts. Now let's run this to the very end. And in this particular case, the time that it took him once he was using the iMachining operations was a total of 11.5 minutes. If we take a look at the actual time we had before on this particular part of about 27 minutes compared to what we have now, it's a total savings of approximately 57%. And remember, doing that on a batch of 120 parts. Okay? Now we'll get back to that again, as I said, at the end. But now let's get to our last part. If I were to open up the last part itself, this part is actually a part that was done in titanium. Now we all know when a machinist hears the word titanium, he starts scratching himself. He says, oh my God, I got to cut titanium. One of the toughest materials that's out there to cut. You need special cutting conditions. You need this extra fluid. You need very good fluid coolant. You need the proper tools. You can't go too fast. You can't go too deep. All of this is problematic with titanium, and you have to know exactly. You have to have a lot of experience cutting this correctly. And not only that, like I said, you cannot go too fast. Now, if we take a look at the part itself. Now, this, by the way, one more point as far as this particular batch that the customer had. He had a first run batch in this particular case of 500 parts. Now, we're talking about 500 parts. Any amount that he would save over here would be a blessing. Okay? So let's take a look at what he did over here. Now, looking at the part, before I continue, if I was to open up the part itself, you can see that the part itself, it's basically just a lot of pockets in here like that, but there's a lot of material that has to be removed. That's the actual part. So let's start by running our simulation on the operations that he first did of the pockets and the profile operations as shown over here. And now we're showing you what was replaced as far as the rough cuts on this part itself. Okay? Using the 2.5D basic operations, running the simulation using Solid Verify, you'll see the following. The first thing he did was work on this side over here. Now note, as he's working, he worked straight across, but when he gets to this area over here, he's coming with the full blunt of the tool into the part itself. Note also, when he gets to this side, he's going straight in. So that's not the best way to cut, but he had no other choice. And the way he has to do it is take small step downs and work slowly. Okay? Finishing this part itself. Let's go now towards the very end. You can see everything was machined out that he had to do. It took him a total of just over 2.5 hours. 2 hours and 33 minutes. Remember, he's doing a total of 500 parts. Okay? Now let's take a look at what we did in iMachining, how we helped him out in the iMachining. Remember now, any savings he got on this part was a blessing. Okay? Now, let's run our simulation using Solid Verify, and we'll start off with the first operation. As you see, when it starts working in this area over here, it uses that trochoidal step over. Okay? You can see it has a constant angle, never over-engaging the tool. When it gets to the end, it repositions itself quickly to back to the beginning over here. So it doesn't go into the material itself, rather repositions itself and always keeps that angle, never going above the maximum angle in this particular case. Now let's run it by a little quicker now as we get further into the part itself. He finished that side, then he did the other side as shown over here. Okay? Doing again those trochoidal cuts, cutting into that area over there as well as around over here. Doing the next area around this area over here. Again, doing this area using trochoidal cuts. Left himself an area over here. That was a complete island cut over here. By doing that, he was actually able to do a morph spiral around that area of itself. Now let's actually finish the simulation over here and see what the result actually was over here in this particular case. You can see the time over here was 57, just about 58 minutes as compared to what we had before of 2.5 hours. Well, that's a total of 62% savings. Now we're talking about 500 parts just on the first batch run. How does this all add up in numbers? Let's take a look at this chart that I have over here. And we'll note the following. Here I have all the parts that I've done. that I showed you today. The first part being 4340, we had a total of 200 parts that had to be machined. Now, the standard 2.5D milling operation cutting time was almost 44 minutes, as compared to just about 7 minutes using iMachining. Now, if you take the entire batch that we had here of 200, it took him, in the standard 2.5D milling, 146 hours, just under 146 hours to machine all those parts. iMachining, just about 21 hours, just under 21 hours to machine all those parts. The saving, as far as time goes, was over 125 hours. Imagine how many shifts that actually is. Cutting time saved, like I said, 84%. Now, we can go even further. How much money did that save him just for the machine itself, just the machining time? I'm not even mentioning now the amount he saved by not changing the tools as often as he did before. Just the machining time saved him on this batch just over $8,000. Nothing to sneeze at. $8,000, just over that. $8,125 he saved just on this batch run. Now let's go to the aluminum parts. The aluminum parts, a batch was 140 parts. It took him 2 hours and 16 minutes to cut that using the standard 2.5D milling per part. Whereas in iMachining, it took him just over 45 minutes to cut that part. If we're talking about the entire batch of 140, the standard 2.5D milling took him 318 hours, just over 318 hours to cut. Whereas in the iMachining, 106 hours, just over 106 hours. If we take a look at the total cutting time saved, that's over 200 hours, 211 hours of cutting time saved just on this particular batch, just by using iMachining. A total of 67%. Now, translating that again into cash, we're talking about over almost $13,715 saved in this particular batch of 140 parts. Going down to the next part, where we had this 4340 part itself, where we had a batch run of 120 parts. In that particular case, the regular standard 2.5D milling took him just about 27 minutes to cut per part. Using iMachining, that took him just about 11.5 minutes per part. If we're talking about the entire batch, the standard 2.5D milling package took him 53.5 hours, just over 53 hours to cut that entire batch. Using iMachining, 23 hours. If we're talking how much time he saved on this batch, it saved him just over about 30 and a half, just over 30 hours time saved as far as this particular batch itself, saving him 57% of the cutting time. Translate that into cash, just about $2,000, just under $2,000 saved over here. But now let's get down to our last part. Our last part, titanium, he had 500 of these parts to cut just on this run itself. Okay? Now, the cutting time per part in the standard 2.5D milling was 2.5 hours. When he used iMachining on this part, that took him just under 58 minutes, okay, on one part. Now, if we're talking about the entire batch of 500 parts, the standard 2.5D milling took him just under 1,280 hours to cut. Translating that into iMachining, doing iMachining on 500 parts, it took him only just over 481 hours to cut. If we're talking about time saved, just about 800 hours. How many shifts is that? If you're talking about 800 shifts, 8-hour shift, that's about 100 shifts. Okay? So we're talking a lot of time over here, about 800 hours of cutting time. Saving him 62% of the cutting time. But let's look at the dollars now. 500 parts, he saved just under $52,000. I know people can buy a CNC machine for that as well. Just for one run, $52,000 was saved just because he's using iMachining. It's just black and white in front of you exactly how much you can save using iMachining. Okay, I hope the picture was as clear as we can possibly make it. And I see there are no questions. So again, that's the end of the webinar itself. The webinar itself will be available as usual on the website itself. Now, one more thing before we end the webinar. Emil had mentioned before about success stories on our success stories. If we go into our SolidCAM site, we have in our iMachining all of the success stories from different companies. It's all listed here. I invite everyone to go in here, read the success stories from all of these companies, and you'll see exactly what we're talking about. Okay, again, thanks to everyone for joining the webinar, and we'll see you again next week for part 2 of this webinar. Take care and have a great weekend.